Hello, everyone. We're Team Atomique, and we're doing QuEra's QRISE 2024 challenge on compilation visualizer. My name is Quinn Manning.
My name is Daniel Shatokin.
My name is Kevin Lee.
Hi, my name is David Nizovsky.
I'm Dmitry Hitrin.
And this is a compilation visualizer for neutral atom gate-based quantum computers.
So our tool incorporates different strategies to enhance control over quantum operation and their accurate representation. And a key aspect of our visualizer is its focus on logical qubit encoding, particularly using the STEAM code, which allows for robust error correction. Additionally, it features circuit decomposition, translating high-level algorithm into executable operations with hardware native gates. And this combination ensures our visualizer not only supports theoretical models, but it also practical for real-world quantum computing applications, including research applications. And now let's see how it works.
So recently, optical tweezers technology has been utilized to enhance the scalability of neutral atom quantum computers. These devices facilitate all-to-all connectivity thanks to shuttling of qubits within the atomic trap, opening up significant possibilities for the application of quantum error correction protocols. However, the complex dynamics of atom shuttling require sophisticated quantum circuit compilation and visualization tools. So in our project, we built upon the compilation strategy presented by UCLA and Harvard earlier this year. You can see what their animation looks like on the slide. Since the pre-existent compiler only supports 2-qubit gates, our goal was to add single-qubit operations into both quantum circuit synthesis and compilation visualizer.
And this is sort of our journey that we took to develop a sort of a novel solution to this. We wanted to start with a user input generic circuit object. So we chose Qiskit, and we wanted the user to basically input any circuit. We'll decompose that circuit into a set of basis gates. We'll run a satisfiability modulo theorem algorithm to find a sufficient solution for the implementation on the atom array. Then we want to reintroduce single qubit gates so that we can animate them down the pipeline. We wanted to implement the STEAM code, which is a quantum error correcting code. And then we wanted to implement stabilizer measurements on those STEAM codes for syndrome detection and error correction. And then finally, we wanted to animate. So here's Kevin now.
So one of our main goals was to have something that is universal and so that anyone can easily use. So through the common used platform Qiskit, we decided to use the Qiskit transpiler plugin, which is able to decompose any quantum circuit into our decided base native gate sets. And so our sets we chose was Rx, Ry, Cz, and Rz can be composed of Rx and Ry. And so how this works is the user can generate any circuit they want in Qiskit, and then through our modified transpiler, it will decompose it and as well as optimize it. Currently, we have it set to use an artificial generic backend for any amount of qubits you want. However, the user can create their own custom backend to suit their own custom applications with their own noises, gate fidelities, just basically making it customizable to their own system. In our example here, we will be taking the 3-qubit W state circuit and demonstrating it on the neutral atom platform. Here you can see we first decompose it from the non-native gates into purely native gates for the neutral atom computer, which is in our basis set.
Just a quick review of the recent work which has been done. There are several constraints that are placed on reconfigurable atom arrays. I think most notably is that an AOD row and column cannot cross over another AOD row and column. So this means that qubits which need to connect to another qubit over a separate AOD channel or tweezer needs to be dropped off in an SLM and then picked up by another AOD. We also assume that arbitrary single qubit gates can be applied. So this is important for our solution on single qubit gates. 2 qubit gates are only applied when the 2 qubits are within the Rydberg blockade radius, which can be found through certain Rabi and detuning pulse parameters. And so our main conclusion is that these constraints work well with logical constraints and can be seen in terms of a satisfiability problem. And we use Z3 solver, as did the previous work, to solve and get an SMT solution. We also reintroduce single qubit gates down the pipeline, which can be done due to the second assumption or constraint on arbitrary single qubit gates.
And with our visualization, the main challenge was to add the animation of single qubit rotations. And we have modeled the behavior and impact of these gates within the quantum circuitry framework. Each gate's implementation is designed to reflect its theoretical operation. So gates can be driven by a Rabi frequency and detuning frequency pulse. But more importantly, we have developed a dynamic animation system that visually represents the state transitions induced by these gates on individual qubits.
So for implementing the Steam code, we first have to take the user's input circuit, and for every qubit that's in that circuit, generate a 7-qubit distance 3 Steam code, which is composed of 7 physical qubits. So to initialize the logical bits, we perform a series of 3 entangling steps and then a final single qubit gate stage. And the stabilizer measurements can be conducted and are written out on the right. There are 6 stabilizer measurements which commute with the logical operators. And it's this that allows us to detect syndromes, which will give us negative eigenvalues if a error is detected. By running all 6 or sometimes less stabilizers, we can detect exactly where the error has occurred, assuming that only one error has occurred, and then correct for it. We were able to write a protocol which initializes the Steam codes. However, due to an oversight on SLM and AOD constraints, we weren't able to animate the full circuit. So that's something for future work. We were also able to implement a protocol for stabilizer measurements on each Steam code in the user's circuit. And we're working on creating a readout zone where an ancilla Steam code can be moved to the readout zone, and then stabilizer measurements can be performed on it for error detection.
We have an
Yeah.
example visualization for a small circuit, and at the top you can see the compilation result, while at the bottom you can see the decomposed circuit with the gate currently being executed highlighted. It's important to know that that's not the original circuit, but the one that's already decomposed, and the gates being reordered according to the output of the SMT solver. Other notable additions include the animation for the single qubit rotations. As you can see here, the Raman pulse parameters are being displayed for the execution of each single qubit gates, and the single qubit gates are being highlighted at the bottom. We've also implemented the measurements for the circuit, which are also being highlighted and are shown at the top by the changing color of the qubits. So that's how our animation looks.
So just as a summary, our approach was to take a generic input circuit through Qiskit, decompose it into a set of basis gates, and run the SMT solver to find an efficient solution on the 2 qubit gates in the circuit. Based on the constraint that we can arbitrarily apply the single qubit gates, we can reinsert the single qubit gates down the line while still preserving order. We wrote a protocol for how to implement the Steam code in addition to initializing the Steam code. And this included the non-fault tolerant initialization and fault tolerant coupling with an ancilla Steam code, which can be moved to a readout zone where stabilizer measurements can be performed. And we hope to build on this by constructing a an easy to use, easy to read, accessible readout zone where stabilizer measurements can occur and users can see where the actual stabilizer measurements are happening and perhaps what kind of errors are occurring and what they're correcting for. And lastly, we used all this and compiled it into an animation, which was shown in the previous slide. And I think that's us. That's our time. So we'd like to thank all of you, and please check out our GitHub. Please check out our LaTeX file. We put in some work for this, so everyone say bye.
Thank you.
Bye.
Thank you. Goodbye.
Thank you very much. Bye.